I think I will be quick about like what is the current state of the blockchain. So yeah, obviously everything is public. We need all confidentiality. I think it's clear. What we try to do with the Zama protocol today is to add a layer of confidentiality. So we are not launching a new chain. What we want is to basically adapt to what is already exists in the blockchain industry. So we often refers to HTTPZ, like you saw, like we have HTTP and then you have HTTPS for the web to add a layer of security. We try to have the same philosophy, like adding a layer of security on top on existing blockchain. So the idea is like you could imagine that any chain and you would have Zama as something on top of it. So, and not like acting as a different chain. So if you think about use case, I mentioned like a few use cases, but obviously you have all finance use case, especially if you think about like traditional finance. If you think about that, obviously you think that everything is confidential, or like most of the use cases in traditional finance are confidential. So this is clearly a big use case, but you can also think about like all things related to governance. Could be like any tokenization of assets, voting, KYC, like any identity, everything on that. And later, when the hardware will be good enough, we'll also have all AI use case. Like imagine that you interact with a machine learning model, but everything is encrypted, and the model doesn't know anything about the prompt, but also nothing about the result. So let's start about the protocol. So this presentation is mainly about like a deep dive about the architecture. So how everything is working under the hood. So we saw like some question about like how many TPS if we are using proof of stake or this kind of thing. So the first thing to understand about the Zama protocol is that it brings like end-to-end encryption for blockchain. And also the good thing with FHE, and we'll see that, is also to have the composability, meaning that before we had like many confidentiality solutions, but you have a lack of composability, meaning that if your confidentiality solution like would work with your smart contract, but probably won't work with another one. So it was pretty limited, but still it was useful. With the Zama protocol, the good thing is that if you use encrypted stuff, you can use it everywhere with other contracts using the protocol or just contract using plain text. So this is great for that. And also what's something we want to emphasize is that the Zama protocol is designed to be multi-chain, meaning that everything you're doing on Ethereum could be done also on any chain tomorrow. So you can think about like bridging confidential stuff. Imagine that you have a token somewhere, confidential, and you want to have this token like bridge to another chain, but keep the confidentiality between the two. This is kind of cool use case you can address if you have a multi-chain protocol. So the architecture of the protocol is split, I would say, in 4 sections. So I'll try to go on each one, but you'll see like it's pretty simple to understand at least like the philosophy of the protocol. So let's start with the host chain, okay? So the host chain is to bring primitive to dApp developer to basically write confidential smart contract. So what we provide is to provide a library in Solidity first to have the possibility to manipulate encrypted uint, encrypted boolean, or encrypted address. The good thing is that we don't modify the EVM. We don't modify the compiler. We are using your classic tools, and it's just working out of the box. So meaning that technically, FHEVM could work on any chain. It will compile, it will be deployable. Maybe it won't work until we are on this chain, but at least technically, it will work. Also, this standardization includes the allowance, because when we talk about encrypted stuff, at some point you want to allow or disallow people to view the value, which makes sense. So obviously we needed also to standardize this ACL logic. So if you have an encrypted value, who can explicitly see the value? So This is what is the allow method. So when you think about like this part, you say, okay, good, I have a library, I can write code, but what happened next? And this is where we have what we call coprocessor. So coprocessor is something pretty new and something that we design like very different from what you probably have in mind. This is not an oracle. This is what we call a coprocessor. So a coprocessor is, I think this is a good illustration of what is a coprocessor. Here you have like your confidential smart contract. So this is like the DApp contract developed by anyone in the assembly. And you maybe use the add function because you want to add two encrypted uint. The library, the FHEVM library, will call a contract developed by the protocol. And basically what will do the protocol and this contract, it will simply emit an event. That's it. So you have like on the coprocessor side, this event listener listening for event coming from this contract. And the coprocessor based on this event, oh, you want to do add A and B. Okay, no problem. I will do the computation. And that's it. Meaning like if you think about an oracle, you have you request something through an event and you expect a callback. There is no callback. Okay? So this is just like I receive event of computation, I want to do add, I want to do a comparison, and the coprocessor will do the computation. The result will be associated with the value generated on chain, and that's it. So coprocessor is just a matter of computation. That's it. And so to have like this computation work smoothly, we don't have one coprocessor, we have multiple coprocessors. So for mainnet, our plan is to have 5 coprocessors. This is not like coprocessor for scalability. This is coprocessor for verifiability. Because like we can't verify computation in FHE today, it's not doable. So what we do is to run multiple coprocessors doing the same work, and all coprocessors will commit on the rollup, we'll discuss after, to say this is the result of the computation, and we are 5 saying the same thing, so you can be confident that this is the correct result. So every encrypted computation is deterministic. So to try to be fast, because like when you think about FHE, you're always concerned about like the speed, to say, hey, FHE is slow. Like I learned about like 3 years ago it was slow, so I'm sure it's still slow. So we have like a full mechanic to parallelize, because the good thing is that if you listen for events to start like doing the computation, you can parallelize. You can be optimist and try to parallelize as much as you can. Imagine that I send money to someone and someone else sends money to someone else. So you have 2 parallel transfers. You can compute them separately. You don't need to wait the previous result to compute the next one. This is a good thing, because when you think about the blockchain, you need to proceed all transactions sequentially. So it means that your TPS will be like slow if you have like many TPS in one block. This is a good thing with the coprocessor design we have. We can we can parallelize all computation. And if we talk about like performance, today on CPU we are at 20, but when quickly during 26 we'll switch to GPU, and one transfer is 22 milliseconds. Like in comparison in plain text, this is slow, but for blockchain it's more than enough. And this is like one transfer. So it means that we can have like 250 TPS for one GPU on one server. So if you want to scale, you just spawn more GPU. So like your limit will be mostly on the number of GPU you want to run to address the load you have. So you can imagine that by design, you can scale to have like 1000 TPS if you need to. Also, the price is great. Like you see, like the price, I can't tell the price, but you see it. It's pretty low for one transfer. It's like the price for computation. So okay, so I think like we saw the computation, but when all coprocessors compute, they commit about the result, because you want to be sure, since we can't verify the result, we want to verify that through a consensus. And this is where the gateway came into play. So the gateway, the idea of the gateway is a simple rollup. Okay, you can imagine that it could be like any service, but in your case, it's a rollup. And this rollup basically will act as an orchestration of the protocol. So it will like verify that all composers compute the same thing, and it will also act as a gateway for any user who wants to use the protocol. Imagine that if you want to have a decryption, the user will simply like call the gateway to say, hey, I'm allowed on this ciphertext and I would like to have the decryption of this one. The gateway, since he has the ciphertext, he also has the allowance of the ciphertext, can say, yeah, you're allowed. I can give you a decryption of this handle. So this is like the main API for user to request decryption, but also for inputs. Because if you want to send an input, you need to prove that you know the value of the input. So if you generate a ciphertext, you need to prove that you indeed know the plaintext value in this ciphertext. So you will also use the gateway to send your fresh ciphertext with a zero knowledge proof to say, hey, this is my input. Can you verify the proof? Returns me like a handle that I can use on chain. And you will use also the gateway for that. And the last piece is obviously the KMS. Because yeah, we talk about like decryption, encryption, but well, at some point we need to think about like private key, public key, and this kind of thing. So for public key, I mean like anyone can have it, it's not an issue. But for the private key, this is more an issue. So what we're using an MPC protocol where we have 13 nodes. And these 13 nodes are just one share of the private key. So no one can actually decrypt something. You need a certain threshold to do the decryption. So in our case, it's 1/3 plus 1. So at least 5 nodes needs to agree to do decryption to actually be able to decrypt something. So for this, for this KMS, it will handle like any public decryption. So public decryption is basically the possibility to decrypt something as a plain text. But if you think about your balance, you don't want to have your balance publicly decrypted. You just want your balance decrypted for you. So in this case, they are also able to decrypt and re-encrypt under a public key you have. So you just provide your public key, and like this, you re-encrypt under your public key. So this is like the 4 components, and this is like the protocol as it is today. So what's next? I think you'll probably see that like during on Twitter, and maybe if you were there on Monday. So we have like 18 operators working on the Zama protocol. So because we talk about like having 5 coprocessors, 13 nodes, okay, it's great. But if all are operated by Zama, it doesn't make sense. I mean, like you want security, so you want to have the 13 nodes operated by different companies with billion at stake, and same for the coprocessor. So we have multiple partners to work on that, and this is already the case for the testnet, where the private key or current testnet is handled by these operators. For next year, and I mentioned that, so today you already have everything on Sepolia, so you can already write contract, deploy contract, do your DApp. Many people did it in the developer program. By the end of the year, we will have the mainnet, and first half next year we'll plan to have the multi-chain and then Solana in 26, because as you understand, like we could do exactly the same on Solana VM or any VM in the end. It's very similar to also like the idea is to have like so today we are around 20 TPS on CPU. The goal is to reach the 100 TPS and probably more, because we did like 250 now on GPU since 1 month. So I should update the slide, but like we'll have more than 100 TPS per chain by 26, and yeah, even more than that when ASIC came in few years. I think that's it. Yeah, same QR code if you want to try the Zama protocol, and thank you.